Good afternoon, everybody. Welcome to class this afternoon. First of all, I want to thank you for watching this, whether you're watching it with me live or you're watching this recorded later on. Really appreciate you putting the time and effort into watching these live streams to get the material. So to start off today, right, I wanted to do something just a little bit different. You'll see that I'm already in a REPL here. I'm going to start off today by writing some code. And I've got some code that I want to write. What I basically want to do is I want to approach one of the lab assignments you all were supposed to do last week. And I kind of wanted to walk through it and do what would be my version of it. And I wanted to try to do it in such a way that we could minimize the amount of code that we need to do in it. So this won't be like a perfect answer to the assignment. So if you're still needing to do it, don't copy this, right? Because it's not exactly what we're looking for here. But I wanted to try to use functions to their fullest ability to write this bit of code in one of the shorter ways that you can do it. So that's what I'd like to start out doing today, is just writing a little bit of code to try to draw that grid that you all had to draw while taking care of functions and using functions to their fullest ability. So I've got my new REPL here. We'll go ahead and zoom into it for you. And I'm just going to start writing some code. So I'm going to start off with my shebang, because that's the perfect thing to start off with, because we're going to keep doing our best practices that are required for all of our assignments. I've got another new best practice that I'm introducing to you all today, and we'll be talking about that in just a moment. So it'll be something new that will be expected in every program from here on out. But I'm going to start off by writing my shebang here. That's hashbang /usr /bin /env Python 3. And let's write some code. So I'm going to create a function here. We'll create a function called def grid underscore row. And I'm going to use some arguments here to help me kind of make my code just a little bit different and make it a little bit more flexible. Because at the end of the day, like, that's what we kind of want here, is the ability to make our code a little more flexible, to modularize things, to use them to where we don't have to kind of repeat the same things over and over again. You know, I'm going to almost bet that there are some of you who ignored the instructions that said write a function, and just wrote me a bunch of print statements to do that grid. And if you did that, that was incorrect. The instruction, you know, in the instructions, it says to write me a function. Now, if you simply wrote a function with some print statements in it, I'll take that. Because one of the big things that I want to see here is I want to see that you know how to write a function, which is what we were talking about last week. So even if you aren't using the function to its fullest abilities, then you still wrote a function, you still met the requirements of the assignment. If you didn't write a function, you missed out on that requirement. So that's going to be an issue. So I'm going to write this function here, and I'm going to use some arguments to allow my function to do some stuff. Now, I've already written this, so I already know what I'm doing. If I were writing this for the first time, what I might do is I might create this function just as like a void function, or excuse me, that doesn't really apply here. I just write this function without arguments and then go back and change the things that I could make arguments into arguments. So maybe we can do that. Maybe we could start out by doing that and then just refactoring this. So we're going to create our function. We're going to call it grid row. And we're going to create some variables to go into it. So we're going to use some of the stuff that we learned in modules 1 and 2 to make us some simple variables that we can utilize So we don't have to type out a whole bunch of, like, we don't have to count all of our dashes, and we don't have to do all this stuff. So I'm going to make a variable. I'm just going to call it something like grid part 1 or GP1. And I'm going to set that equal to a plus sign that will concatenate with that minus sign and a little space. And in fact, I might also want to put a little space here. And I'll use my repetition operator. And we'll put a number in here like 6. So now I have this variable here. So now if we print this variable, print GP1, we can see what this does. So I also need to call my function. So let's call that function grid row. So we get this grid part. Now that's all well and good, right? But we need this to be repeated a few times. And so we will be able to do that, right? Because all we would have to do here would be to create a something else where we would be taking this GP1. So maybe we can say GP1 underscore line and setting that equal to GP1 times 3. So we're using that repetition operator again, because this expression is giving us that string. And so now we can take that string, we can multiply it 3 times and have it 3 times across. And so if we add that in here and check that, then we get that line across, with the exception of one thing. We're missing that plus sign at the end. But we can simply add that with concatenation. Plus that plus sign. So now if we run that, we get that whole top. I've not counted anything. I've just decided that I want it to be 6 times. So I'm not having to sit here and go 1, 2, 3, 4, 5, 6, 1 space, 2 space, 3 space, 4 space, 5 space, 6 space. This is programming. We're using the ability to code and the things that we know to solve our problems by making our life easier. So now we have that one grid part. We're ready to go with it. So now something else that we can do is we can make another grid part. Because another thing that we had set up for us would be those lines where we just had the bars coming down. So I could just take this for grid part 2. Right, so we'll copy this. I'll make a GP2 and set that equal to that bar character with a space plus a space character times 6. And so now we can create a GP2 line in a similar manner. GP2 underscore line equals GP2 times 3 plus the concatenation of a bar character on the end. So that bar character. So now I can print my GP1 line and I can print my GP2 line. And we can see how that looks. Okay, so not enough spaces here, right? Not enough spaces between our characters. But that's the place where we know, oh, well, I can go back here and I can adjust this, right? And instead of adjusting it once, I can just adjust it, or instead of adjusting it multiple times, I can adjust it once by adding an additional space in that space character. And now we have that part of the grid. Now we can do something even better. Because I can take and do something that we talked about back in Module 1, and I can put an escape new line character here at the end. And so then I can create a kind of this cell height variable. So we'll even call it cell underscore or grid, cell underscore height equals GP2 underscore line times 3. Right, and so this will give me 3 of these lines. So now if instead of GP2 line, we type cell height and see what happens. We get 3 of those. So now we have something that's pretty interesting here. Right, we can start to make this grid. And we can start to see the variables that we can use. Right, so I'm going to do this the way that we would know now. I'm not going to use any loops or anything like that, even though I could. So what we'll do is, in addition to this cell height, we will also add the bottom row, which we've already made. It's called GP1 line. So we can add GP1 line. We can concatenate that. So now we'll have the top, we'll have our row, we'll have a bottom. Since we have this new line character here, you can see the blank line here. I can run that. And now I have a row. So that's good. So really what we would want to do here is we could do even more with this if we wanted to, right? Like we could concatenate another escape character. To the end of this. So now it'll put us an empty line on the end of this. But now what we could do is take all of this and multiply it by something. So we could call this rows, set it equal to cell height, and I put that in a string when I didn't intend to, cell height times 3. And now let's print out rows. Would you look at that? We have ourselves a grid. And now it's time for the most powerful thing about this. Is because since I didn't sit here and do bloody, 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 blah, I have 3 arguments that I could make here that I could use to change my grid on the fly if I change some of these numbers that I have in here into arguments. You see right here I have the rows. So I could change that to num underscore rows. And I could put an argument for that here in my num underscore rows. I have this cell width here. And I have this, I guess the other one would be like a column width. So we can call this C underscore width. And that number is going to be the same as that number. And I guess this would be our row width, so we could call it R underscore width. And we can make that number the same as that number. And so now we can add these numbers here. C underscore width, comma, R underscore width, comma, and num rows. Now I've got this number here, GP2 line is 3. And so that was giving me, yeah, that's my height. So I can add another one for this. We can call this C underscore height. And add that in here as an argument, C underscore height. So now we have this versatility, right? So I can say C width, R width, C height, and num row. So I got my cell width, my row width, my cell height. I can just add some numbers in here. 3, or I think it was 6, 3, 3, 3. We'll start out with this and run this. And that gives us the exact same grid. Now, if I want to recall this grid and have it something different, we can do this here. Maybe I want to make it smaller. Let's make this 4. Let's make this 1. Let's make this 3, and let's make the other 2. Let's leave the other couple at 3 and just see what happens. I just kind of want to test this just to see, because I'm kind of doing some of this on the fly here. So let's run this, and there we go. We've got a singular grid, right? Because that column width is just one column. Or that row width is just one, because it's cell width and row width. So that should probably be like column width or col width. So we can change that. Give it a better variable name. And I mean, that's part of programming, is that you're going to refactor as you code. So that column width gives me one column. That cell height is 3. And that number of rows is 3. Like if I change the number of rows to, let's say 2, that should drop it down to 2. If I change the cell height value here to be 6, that should make my cell taller, and we can make my cell wider. And so I can call this as many times as I want, using different numbers here, and get completely different grids. So let's just put in some random values here. 2, 8, 3. We'll do one that's like 3, 4, 5, 6. So this is the real power here, right, of these functions. Because I've made this function, I've done it with arguments, so now when I call it, I can call completely different grids just using arguments in my function call. And so this is a whole lot less code than having to go through and write a print statement for every one of these lines. And it's a whole lot more versatile. So like if I run this, right, we're going to see all the different kinds of grids that we can get out of this, which is pretty good. So this is one of the most efficient ways to write this code, at least with knowing kind of what we know about it. Like we could add some other sorts of data structures here that would make it easier, that would allow us to do it a little bit quicker. But for what we know so far, here in really less than 18 lines of code, because we have 1, 2, 3, 4 blank lines, and then one of our lines is the shebang. So if we take those out, we have 13 lines of code where we have a completely versatile grid that we can make look like anything. So ideally, when we're thinking with code, when we're doing that programmatic thinking, this is where we're going to go, is towards something like this. Something that's versatile. Something where we don't have to go in and edit the source, edit any of this to get something that we want. Because I could take that function, plop it into any program I want to plop it into, and based on what I call, when I do my function call, I can make it a completely different size of grid. And so this is something that we want, ideally. So that's pretty cool. I'm going to name this one just so I can have it saved, because I'm going to want to make multiple REPLs today, because we've got a lot of programming to do. But before I move on, I kind of want to show you one of the new data things that we're going to do, or a new best practice that I want you to do. And so I'm putting it here at the beginning, so I'm trying to make sure that you watch it. And that is the main gate. So I'm going to talk about the main gate a little bit, then I'm going to add a main gate to this program so you can see where it is. And then in the other programs that we do today, we'll also be doing the main gate in there. So let's talk about the main gate. So there's a concept as we approach programming, and programming in Python specifically, where we talk about the main gate. And I have the line of code that is the main gate here on the screen. It's this line of code right here. If underscore underscore name underscore underscore equals main. And we talk about it in relation to this module because it's a conditional statement. It's an if statement. So it's checking a condition to see if it's true. And we'll talk more about what that means here in just a few moments. But this statement is something that I'm going to expect you to have in every single one of your programs from here on out. And what it does is it separates the functions of our program from the parts of our program that do stuff. Right? It separates our functions from our actual running code. So, for example, in the program that we just did, I would separate my functions with my function calls. I'd put my function calls behind the main gate. So why would we do that? What does this do? Well, what this does is essentially, before executing code, right, the Python interpreter reads the source file and defines a few special variables and global variables. And one of these special variables is name. And if the code is in the file that you're running, right, the file that you're running is giving the name of main. So if the Python interpreter is running that module, that particular source file, as the main program, so like when you're writing the program and you go up there and you click run, that's what we're talking about here, is running that file within the main program, that name variable is given the value of main. Now, if you take this file and import it into another file in a similar way that we did import math last week. If you take the file and import it into another file, then anything that is behind that main gate won't run. So you won't be running extra code that you don't need. Like if I write some code in that program that we just did to display a grid, and then I'm like, I want to display a grid in this other program. Oh, I already have my grid function that I've already written. I can just import that in. If I don't have that main gate, all the other code that I wrote to show all those grids will run and execute in that new program, even if I don't want them to. Because it's going to execute all of the code from the imported files and the main file when I only want it to run the code that's inside of the main file. If you've done any Java before, this would be kind of like the main method works in the Java programming, although this isn't a strict requirement. So really here we go. We can say, I just show you this here, which is basically kind of what I just said. We can write a function. We can import it into another function. And if we don't want that code to run inside of the other program that we are importing it into, we put the main gate on there. So we have some advantages of using the main gate here. And so by default, every Python module has the name that is main if that's the file that's running. And that implies that the module is being run standalone. So if I'm running the file standalone, I want this code that's behind my main gate to run. If I'm importing it into another module, I don't want that code to run. And this gives us reusability, which is enormous. We can take one script and we can use it as a reusable program or a standalone program, either way we want to do it. Like this is a huge thing. This is why I want to see this line of code written in every program that you do from here on out and have the function calls and all the running code behind that main gate and all of your functions that you've written above outside of that main gate. So for example, if we were going to do that in the program that we just did, I would write a line of code down here. If underscore underscore name underscore underscore equals equals underscore underscore main underscore underscore colon. And now since I've written this conditional statement, something that we'll talk about more in a little bit, everything that's under a conditional statement that is a part of that conditional statement has to be indented in the same way that we indented our functions. So I run these over here with an indent. And so now what we have here is the exact same program, right? Like if I run this again, I'll go ahead and clear the console so you can see the proof. If I go ahead and run this again, it's going to give me the exact same results. But if I take this file and import it into another program, this stuff won't run since it's behind the main gate. We call it the main gate because it's kind of it's locking this part of the code out, or maybe locking it in. I guess it all kind of depends on your perspective as to whether the main gate locks something in or locks something out. It's locking it, I guess we could say locking it into this program or locking it out of the program that we're importing it into. Right, so that's the big purpose of this main gate. And we're going to use it in every program from here forward. So that's important. So now that we have that, we can go ahead and start talking about conditionals and recursion. So now that we've talked for a half hour, we can go ahead and focus on the material that we need to be focusing on. So conditionals and recursion, and this is where we really get into programming. Like this is where we're kind of taking it to the next level, right? Because so far we've just kind of been doing some basic stuff, right? We've just been, writing statements that are like equations. We've been creating some variables. We started writing some functions. But now we're going to get into the big thing, which is going to be conditionals. And when it comes to conditionals, our conditionals have one big purpose. Sometimes we want our programs to be able to make a decision. And so we use our conditionals to allow our programs to make a decision, to conduct this decision-making process. So up until this point, when we kind of look at the data structures of our program, everything that we've done so far has just been a linear structure. Our interpreter reads everything from the top to the bottom, and it just kind of goes through everything. But now, at this point, we're moving past that. We're moving into something new, and we're giving this conditional structure to it. And when we have a conditional structure, we have kind of a tree-like pattern, a decision tree. And so certain conditions will be met, and certain conditions will not be met. So there'll be parts of our code that'll be ran, and other parts of our code that won't be ran. And so as we're writing our conditionals, we have this syntax here. If some condition, right? Like if x is greater than 7, if name equals main, if whatever, if we have this condition, if that condition is met, then what happens is that condition evaluates to true. All of our conditions evaluate to some kind of Boolean expression, whether it's true or false. So this is where we get to kind of the point of the last 3 weeks of discussion assignments, where you've been looking at propositions and you've been doing truth tables and you've been kind of discerning what these things are. Because really, what is a proposition except for a condition? And so we said when we're looking at something like a condition, it is a proposition. It has no ambiguity. No ambiguity in a condition. Right? A condition must evaluate to either true or false. It doesn't matter which one it evaluates to, whether it's true or false. A non-issue, right? But it has to evaluate to one or another. There's no in between. It's binary, right? Zeros and ones. We're not quantum computing here. There's no twos. There's no state where something is simultaneously true or false. It is simple binary. So our conditions have to evaluate to either true or false. And then you have to have one statement inside of each branch. So if I have an if statement, I have to have some code that goes with it. If I have an else statement, I have to have some code that goes with it. Now we can chain conditionals, which is writing if, elif, and else statements. Elif standing for else if. Or we can nest conditions. So if we kind of look at those in terms of like a structure, when we're talking about chaining conditions, we're talking about having a series of possibilities for one condition. So we have one input, and it's evaluated against a bunch of different conditions, and each of those conditions has its own output that'll be met if that condition returns true. Our nested conditions or subconditions have conditions under conditions. So I might have an if statement that evaluates to another if statement that evaluates to another if statement that evaluates to another if statement. I can chain or nest my conditions as many times as I want. Now, when we're looking at these Boolean expressions, a Boolean expression is, as we've said, an expression that is either true or false. And when we were making this evaluation, when we're evaluating our Boolean expressions, we use the operator equals equals. Or that's one of the things that we can use, is equals equals. And like I bring it out here on this own slide so we can make a distinction between equals and equals equals. Because these are two completely different things, and you don't want to confuse them in your program, or else you're going to cause yourself a bad time, right? We use our equals when we are working with variables. A single equal sign is for assignment. So when we have this single equal sign, what we're saying is we're saying whatever variable is this other variable. It's assignment. We're taking that data that we have on the right-hand side of the equal sign and we're putting it inside of that container. Our equals sign is evaluation. We're asking the question, does this equal this? And the result is going to give us a true or a false. Now, in addition to our equals, we have some other relational operators. Exclamation point equals is not equal. So if we were looking for a condition where two numbers were not the same, or two strings were not the same, we could use not equals. Then we have greater than, less than, greater than or equal to, and less than or equal to. And these are all evaluative. You did your truth table last week. In doing your truth table, this is what we were looking at. Is this equal to this? Is this not equal to this? Is this greater than this? Is it less than this? Is it greater than or equal to this? Is it less than or equal to this? With these relational operators, we're looking at that truth table and we're evaluating an expression of true or false out of either of these. Now, in addition to these relational operators, our Python also has logical operators. And so with these logical operators, and, or, and not, right? With the operators and, or, and not, I can take multiple conditions. Remember compound propositions? I can take multiple conditions and evaluate them. I can say, and we can look at this in like the way that we'd look at English. So I can look at x is greater than 0 and x is less than 10. So in this case with our and, both conditions must be true. If I use or, well, it's one or the other. So either condition can be true. And if I use not, well, not negates a Boolean expression. So if I say not x greater than y, that means that y is greater than x to evaluate for true. And so these are things that we need. So what I want to do here is I want to write a program. We're just going to move on. We're going to spend some time in writing a program so we can get a little bit of experience with chaining and nesting conditionals. And we're going to do both in this program. And we're going to write a program that's going to determine a leap year. And I have my algorithm here for determining a leap year. So determine whether a year is a leap year, right? So I guess before we start writing this program, we need to talk about what a leap year is, right? So we say that, a year is 365 days, that it takes 365 days for the Earth to travel around the sun, but that's not exactly true. It's more like 365 and a quarter days. So that's why every 4 years we have a leap year. Last year, 2020, we had February 29th. That's where we add that day because it's the shortest month. Last year was a leap year. This year, not a leap year, because it's only once every 4 years. So if the year is evenly divisible by 4, we progress. But if it's not evenly divisible by 4, we go to step 5. This is our algorithm, right? These are the steps that we have to take to solve this problem. So if the year is evenly divisible by 4, we can go on to check some more conditions. If it's not evenly divisible by 4, then we can go ahead and tell the user that it's not a leap year. So cool. So if it is evenly divisible by 4, we're going to check to see if it's evenly divisible by 100. If it is evenly divisible by 100, well, we can move on to step 3 and evaluate something else. If it's not evenly divisible by 100, then it is evenly divisible by 4, but not evenly divisible by 100. We can go on to step 4 and see that that year is a leap year. Now, if it's evenly divisible by 4, evenly divisible by 100, and evenly divisible by 400, then we can say that it is a leap year. Otherwise, we can say it is not a leap year. So when we kind of look at the chained data structure, or when we look at the structure of this program, chained and nested conditionals, we see something like this. Like we get this input, and then we have 2 possibilities from step 1. So in step 1, I have 2 possibilities. Either I get to say that it's not a leap year, or I have to check 2 more conditions. So it goes into another condition. Now from here, I check my condition. In this case, if the condition evaluates true, then it is a leap year. Or if it evaluates false, then it is a leap year. If it evaluates true, if it's on this no side, we have to check 1 more condition. And from here, we either get yes or no. So let's just write this program. So I'll create myself a new REPL here. We'll call it leap year. And I'll have to put some special characters on this because I do this program a lot. Sp21 OL. All right. So what I'm going to do here is I'm going to add my shebang, because we always start by adding our shebang. So that's hashbang /usr/bin/env python 3. And I'm going to write a couple functions here. I'm going to write a user input function. So we're going to write a function for user input. We'll call it input year, because we're going to do something besides just get the input, although we'll pass the message to our user via the argument. And so what we'll do here is we'll set a temporary variable, we'll call it x, to input message, and then we'll return the integer value of x, because we have to typecast it, right? Remember that everything that we bring in via input comes in as a string, and if we have a string, we can't do math with it. So if we're going to need it to be a number, we need to typecast it to an integer. So we're going to return it as an integer here. And so now we can start to write our find leap year function. So I'll create a function def find underscore leap underscore year. And we're going to bring in an argument of year. So from here, what we want to do is we want to kind of get that conditional structure and use that conditional structure to evaluate some statements. Now we have the perfect mathematical operator to do this because we have the modulo. Now remember, the modulo finds whether or not one number can go into another number. You know, how many times it goes. You know, it's the division problem, but instead of giving you the result of the division problem, it gives you the remainder of the division problem. So if that remainder is 0, then we know that that number goes into the other number evenly. So we can write our first set of conditions here, and I'm going to write them a little bit weird from the way that we normally write them, because I'm going to write the conditions where we're at in our program all at once. So we're going to check the condition if year, which we're bringing in through our argument, modulo 4 equals 0. So we're going to check to see if 4 goes into the year evenly. If it does, we're going to write a condition there, and that condition is going to be more conditionals. If it doesn't, that's going to be what our else statement is for. So else, when we write else, it's all other conditions, right? So if year modulo 4 is 0, then we're going to do something. We're going to put that under the if condition in just a few minutes. If it's not, if it's any other number, we're going to print not a leap year. Now, if it is, what we said we needed was we needed another conditional. And notice here that when I'm under this condition, I've indented in. And so with each level of a condition, I'm going to indent in again to show that the code that I'm writing belongs to that condition. So we're going to check for the next thing, which is if year modulo 100 equals 0. Now in this case, we also had an else condition, right? So else print it is a leap year. So if it's divisible by 4, this code runs, because this code evaluates to be true. We have this indented underneath this if statement. If this is false, then it skips down to the else statement. So the same thing here. So if this is true, then it's going to check and evaluate this to see if this is true. If it's not true, it is a leap year. If it is true, we have to write another condition, which in this case is our final condition. So if year modulo 400 equals 0, then we can print it is a leap year. Else, we can print not a leap year. So this is our algorithm. Fleshed out into code. So the big important thing here to pay attention to is the structure, right? We have this if statement and this else statement. They're on the same formatting level. They're indented the same amount. That means they're a pair. Everything that is indented underneath this if statement belongs to this particular if statement. So this if statement and this else statement. So on the condition that this if statement is true, it's going to run this other set of code. Now in this instance, we're evaluating another if statement. And so underneath this if statement, we have this if statement and this if statement. So to get here, this condition has to be true, this condition has to be true, and this condition has to be true. right off the bat, if this statement is false, then we jump down here. If it's true and this statement is false, then we jump to here. And if that's true and that's true and this is false, then we jump to here. So that's the structure here. So we've got this nesting several layers deep. We have this chaining several layers deep. So this is kind of a good program to show some logic. In our program that has to do with conditionals. So now we're going to write our main gate. So I'm out of I hit my backspace key, so I'm all the way back and I'm all the way out. And I'm going to write if underscore underscore name underscore underscore equals equals, and in quotes underscore underscore main underscore underscore and colon. And in the event that we're in the main file, if we're in that current file and we're running this program from this current file, which we are, we're going to take a variable user underscore year. We're going to set that equal to our input year, our input underscore year with the value of enter a year. That'll execute our input year function, get the year from our user, pass it back as an integer. And then we'll take that value and that user year value that we get returned here, and we'll pass it into our find leap year function. Find underscore leap underscore year with user underscore year. There. So now we have our entire code. And I'll zoom out and kind of put it all on the screen here so you can kind of see it. And we'll run this. It gives us enter a year. So we'll start out with the current year because we know that this year is not a leap year. So if we enter 2021, we should get that it's not a leap year because it's not. So we know that it evaluated this correctly. We know that last year was a leap year, so we can check that. And we get it is a leap year. So based upon that, we know that our conditions are working properly. And we can put whatever year that we want in here, whatever year that we might be curious about, like maybe, 1960, let's say. 1960 was a leap year. Now, there is some stuff that I won't do right now that we could do. So if you were working on this and you want to kind of extend yourself, one of the things that you could do here is try to extend this program to give you a different phrasing based on whether the year is past, present, or future. So like if I wanted to look at 1960, I could have it say it was a leap year. Look at 2021, I can say it is not a leap year. And if I look off in the future, I can have it say it will be a leap year or it will not be a leap year. So if you want to try to practice and extend yourself, and in doing that, that's something that you could try out with this. And in fact, you know what I think might be interesting? If you want to try that out and submit it, I'll give you, say, what would be worth it? Maybe 10 points on your on one of your labs this week. So if you can send that to me in an email by Sunday at 11:59 p.m., I'll give you some extra credit points on your one of your labs this week for extending this program to also include that sort of terminology where it was a leap year, it is a leap year, it will be a leap year, based on whether the year is before the current year, is the current year, or will be the future year. I won't get into that now because I am short on time because we've almost been an hour here, and I still want to cover some stuff. Because I still want to talk about recursion. And so what is recursion? Recursion has to do with functions. Because one of the things that we said last week was that you can call a function from anywhere. You can even call a function inside of itself. So I can have a self-referential function, and when my interpreter hits that function call that's inside of itself, well, it's going to restart that function, and it's going to, in essence, create a loop. And all kinds of problems in life, we can define them in that sort of way. We can define them in terms of themselves. So we have like an English compound sentence. That's two sentences with an and between them. Or, you can think of it as like two mirrors facing one another. And when we get into the next module, we'll be talking about a while loop. And a while loop and recursion are similar concepts. Where you can use one, you can oftentimes use another, but it's not always the case. There are some problems where using recursive functions versus using a loop is more desirable. Now we have three laws of recursion. One is that there must be a base case. So this is why we wait and talk about recursion in this module, because we need some kind of case, we need some kind of condition through which the code can run where it won't call the function again. So we need some kind of condition, we need a conditional where it'll actually stop the recursion. Because if we don't stop the recursion, we get what we call an infinite loop. Now in Python, Python's a little friendly. Python has what they call infinite loop protection. So it'll run a little while before it just errors out and tells you that your program won't run anymore. But in other programming languages, if you end up with an infinite loop, what it's going to do is it's going to crash your program, potentially even crash your system that your program is running on, so it can cause a lot more issues. So we want to make sure that we have a condition that will be moved to where at one point we're going to break that condition to stop the recursion. We also have the recursive case, which is a line of code that calls the function from within itself. And then in that call, we must have some kind of argument that we're moving toward that base case so we can break that condition to where that condition maybe at once was true, but now it's going to be false. So let's do just a little simple proof of concept for recursion here, just so we can kind of get an understanding of this. And I think it'll probably be enough to kind of move you in the right direction for what you need to do for your lab that involves recursion this week. So I'm going to create myself a new REPL here. And we're going to call this recursion underscore example. Or actually, I put that in the wrong box. Python recursion example create. And we're just going to do a simple countdown recursion here. So we'll start off with our shebang, hash bang, user, bin, environment, Python 3. And we'll write our function. We'll define a function called countdown. And then we'll give it a number. So we'll give it an argument of number. So we want to count down from whatever value our user enters to 1. Let's not count down to 0. So we can say, we can add our condition here. Of if num greater than 0. What we'll do is we will print num, and then we will call our countdown method from inside of this current method, and we'll say countdown num minus 1. So we're bringing in a number. Let's say, for example, while we're talking about this, let's just say the number is 10. So when we call our function, we'll call it with the number 10. So we'll say if 10 is greater than 0, we'll print 10. And then we'll run the function again with the current value of number minus 1, which at that point it becomes 9. So then when it recurses the function, it changes, and now the num is 9. So we're saying 9 is greater than 0. So what we're doing there is we're moving the argument each time to get closer to 0. Because right here it'll print 9, and then it'll recurse the function with 9 minus 1, which is 8. And that's 7, that's 6, that's 5, that's, the next one is 4, the next one's 3, the next one's 2, the next one's 1. And when num is 1, it'll go 1. 1 is greater than 0. It'll print 1, and then it'll run countdown again with 1 minus 1, which is 0. So at this point, num is 0. 0 is not greater than 0. 0 is equal to 0. So it breaks that condition. So we can just write another statement here and like an else statement. We can print blast off. Right, so let's put some code behind a main gate here so we can see this function, right? So if name is main, we'll just get an input from our user the simple way for right now. We'll create a variable called starting number, and we'll set it equal to int input, enter a starting number, and then we'll call that countdown function with starting number as the condition, or as the argument rather. So now, and we can almost see this all zoomed in on one screen. Now, whatever number our user puts in, that's going to be the starting number. It's going to go through our condition. Each time it's going to check it. Each time it's going to subtract 1, and it's going to redo the program again. So if I run this now, I get enter a starting number, and I'll enter 10, and I get 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, blast off. Beautiful. Right, and I can put in whatever number I want here, and it's going to count down from that. And so I could even do things like chain and nest conditionals here. Like I can say like, oh, if num modulo 2 equals 0, then we can print num and take that countdown recursive call down by 1. Else, meaning if it's an odd number, I could just print odd. Right? So this is just nesting some conditions in there. I would also want to do countdown num minus 1 here as well. So that way it has that recursive call in it, or else it would just stop. Right? So now I can run this. I can enter, let me clear this out. I can run this. I can enter that starting number. I can enter 100 again. So now every odd number will just say odd, and every even number will be the number. Pretty cool. And so that's going to kind of be a little hint, a little wink and a nudge toward your big recursive lab that you're doing this week. So that's all that I have for you for this week. We've already sailed way over time that I normally like to do this. So we will stop here. I'll hang out in the chat, turn the music back on just for a couple minutes, just in case anybody here live has any questions. If you're watching this recorded or you think of questions later, feel free to ask them. But again, that's all that I have for you for today. Thank you for watching, and we'll see you next time.